Log on, tune in, find out. Another good idea from Cambridge.
Earlier, some of the talks we're going to hear this week and some of the discussion are focusing on this issue of climate tipping points. And we're hoping that the seminars we hear and the discussions we have will sort of lead us into a more robust understanding of those and how we get forewarning of them. And shortly after our kick-off meeting here in August, part of which was about tipping points, I saw Peter Reid speak at an Exoplanets conference in Exeter about the subject of this seminar, which is about regimes of atmospheric circulation. And it struck me as almost the most extreme case of a tipping point in the climate system. So I thought we'll get Peter over here to explain his findings, and then we'll see if we can connect it to what some of us have been thinking about with regard to tipping points. Okay, all yours.
Okay, thank you, Peter. Well, I should say thanks indeed for the invitation to come and talk to you. This afternoon now, I suppose, isn't it? So my background in all of this, I guess, is I'm an atmospheric physicist. I work a little bit with atmospheric models and such like. But I sort of work at the kind of crossroads between fundamental GFD and the dynamics of all planetary atmospheres that I can lay my hands on, not just the Earth. The Earth, you can view as a kind of sort of special case. And just recently there's been a considerable growth, at least in my perception anyway, in interest in doing what's called comparative planetology. So this is really trying to sort of look at the Earth's atmosphere and looking at the other atmospheres that we can study and trying to learn from the sort of similarities and differences that we find, which is an idea that's been around a long time, but it just seems to have suddenly got a kind of new injection of interest for various reasons, and some of these I'll try and explore with you today. So this is by way of a kind of bit of a mixture of a talk. There's a bit of review material that I'm going to introduce here. There's a little bit of sort of work in progress, which is mainly where my student Yixiong Wang, Chinese student who's just been with me for just 1 year so far. So this is very much sort of his some of his project work, which is obviously still developing, but nonetheless I hope the results will be of some interest to you to see where we're going, and I'm obviously interested to sort of get discussion and feedback from people as to where we might go from here. So this is the title that Peter gave me, looking at regimes of global atmospheric circulation in the kind of widest sense. And there are various motivations behind all this stuff. So as I say, I'm shamelessly coming from the sort of the planetary world in part of the motivation for some of this work. So we now know, as a result of the 50 years of the space age or whatever, that the solar system presents us with something like 8 well-established planetary bodies that have substantial atmospheres, including the Earth. And just as an example, okay, this is the familiar one, which I don't need to explain too much to people here, I guess. This is a temperature distribution as a function of latitude and height. This is the equator in the middle there, going all the way up into the mesosphere. The zonal wind pattern, the zonal wind, and the meridional circulations. These are all taken from essentially the Era 40 data set, familiar to many here, I'm sure. But we can look at other planets in the same kind of way. This is the atmosphere of Mars, viewed more or less in the same kind of manner. This is using the Mars climate model that my group, together with several other people, a group in Paris and the Open University here in the UK, have developed over the last 10 or 15 years or so. So we have a reasonably complex and sophisticated model of the Martian climate. And this is the kind of sort of annual average kind of pattern that you see on Mars. Looks surprisingly familiar. It's actually in a very, very similar kind of circulation pattern to what we're used to on Earth. But the other sort of well-known planet, I suppose, is the planet Venus. And Venus is in a very different kind of regime. It's a very, very slowly rotating planet compared with the Earth, even though the planet itself is roughly the same size and an organisation as the Earth. By rotating very much more slowly than the Earth, then you find very, very little horizontal temperature contrast, for example, between pole and equator. and it has these very, very strong super-rotating zonal winds. If you actually look at the planet, you see it's completely cloud-covered with very characteristic sort of Y, or sort of looks like a kind of a Y or U-shaped pattern of clouds that are at quite high altitude, roughly 50 or 60 kilometers above the ground. And the basic circulation is tremendously dominated by large, almost planet encircling Hadley circulations, with something interesting going on near the poles that I'll say a little bit more about as we progress. With respect to the background stars, Venus rotates roughly in 240 days, Earth days. So it's 240 times slower than the Earth. Though the planet itself is not. No, in fact, it seems to be in a rather subtle and not very well understood resonance with the Earth, in fact, in a sort of ratio of simple integers. But it's certainly not one-to-one with either the Earth or the Sun. And although it does rotate backwards, that's another kind of weird feature of it. So that's why I've shown these here, as I've shown them here.
Year?
Sorry?
What is its year?
Its year is, oh gosh, I can't remember exactly off the top of my head. It's roughly 2/3 of the Earth's year, because it's some way closer to the Sun. Mm-hmm.
When you say it rotates backwards, how would you know which way is up?
Well, in the sense that the angular velocity of its rotation points in the opposite direction to the angular velocity of its orbit. So that's what I mean. Whereas every other planet in the solar system, they're parallel rather than anti-parallel. Okay, so that's just by way of a bit of orientation. So this kind of raises clear questions that they're being observed and they're being modelled in increasing detail these days. And we'd like to be able to understand their circulations in a quantitative way and to be able to compare them quantitatively. And it does raise the question, can we really regard these as essentially the same experiment being done under different parametric conditions? Of course, there are many similarities, but there are also many differences. The atmospheres are made of different material, they're different locations with respect to the Sun, they obviously have different surface topography and so on. But this is really trying to get at the question as to whether there is a kind of grand picture within which we can understand not just the Earth but all planetary atmospheres. That's our grandiose goal, perhaps rather arrogant goal, perhaps one might argue. So there's another set of motivating questions that is probably why this comparative planetology issue is becoming quite fashionable. That, of course, is that we're now in the era where people are actually discovering and starting to study planets around other stars. And these are being discovered at a prodigious rate. There's probably between 300 and 400 planets that are now known about, and even that's probably out of date by now. These raise all sorts of other questions. Of course, the astronomers are desperately trying to find Earth-like planets that might conceivably harbour life as we know it, Jim. And this is one particular example, this so-called Gliese 581 system. And actually this slide is already out of date because this actually shows, 4 planets, rocky planets that have been discovered around this star. In fact, there's probably about 7 that have been discovered now as a result of recent observations. But these include planets which are between 5 and 10 times the mass of the Earth, including a number that are very, very close to this magic sort of Goldilocks region, the so-called region which is close enough to the star where, in principle, it's suggested that liquid water could persist. And so this is the sort of the holy grail of exoplanet discoveries, trying to find planets in the habitable zone. And in fact, this particular one, 581d, was the one that generated a lot of interest recently. That was even suggested it might even harbour a water world type of planet. It was a somewhat fanciful artist's impression, based on, of course, a huge amount of imagination and not very much science. So that's by way of the sort of second set of motivating questions. So these are the sort of supplementary issues. So these circulations of these planets, of course, may sample a much wider range of parameter space than we might find within the solar system. And it's obviously begs the question as to what we can say about their atmospheric circulation and climate, despite the fact that for the foreseeable future, we're only going to be able to get kind of disk averaged or disk integrated measurements. We're not going to be able to sort of plot details very readily on the disks of these planets to say very much about the details. So we'd like to be able to make absolutely optimum use of all the information that the very limited information that we can muster. And of course, it does raise the interesting question as to what are the key parameters that astronomers should devote their efforts to trying to measure. And so this is partly what underlies where we're coming from. Cool. Of course, there's a third set of motivating questions, which of course is perhaps most relevant to this program, which of course the Earth's climate being slowly perturbed by all sorts of factors. And I couldn't resist putting this in, I suppose, from Tim Lenton's recent paper, I guess, about the idea of tipping points and catastrophes and so on associated with the MOC, the thermohaline circulation, and looking for evidence of bifurcations, sudden changes, and multiple solutions, and all that sort of thing within the climate system itself. So here's my take on these motivating questions. So how does the climate respond to changes in these forcings? Will they happen smoothly and continuously, which you could regard as a sort of safe changes, or in sudden and discontinuous bifurcations where things may happen more catastrophically? Is the climate system hysteretic with these multiply disconnected solutions, for example? And again, what are the key parameters that we need to understand? So this is just by way of background, and part of the interest here is trying to identify what are the key dynamical similarity parameters that we might need to focus on. Well, part of my background is not just in the sort of atmospheric science world, but also looking at laboratory analogues of atmospheric circulation systems. Now, this is a venerable activity that's been around, I guess, in a serious way for something like 60 years or so, and I'm just sort of the inheritor of such a tradition. But there are a set of experimental systems, experimental fluid experiments that one can investigate that are, in a sense, a highly non-trivial toy model in a certain sense. They obviously contain many fewer complications than one is used to dealing with in the full climate system, but on the other hand, they're real fluids with all the non-linearities that entails, and so they are rich systems in their own right that may exhibit some of the qualitative kind of phenomena that may be of interest to us. In particular, this particular system where we can imagine taking the sort of middle latitude regions of a planet like the Earth, kind of unfolding them into a cylindrical domain. We have to do that in the lab because we actually want gravity to act essentially always downwards, and to create a spherical system in a terrestrial laboratory with gravity acting always inwards towards the centre of the sphere is something that's actually rather difficult. Nobody's actually come up with a good way of doing that in a terrestrial laboratory without sending it up into space, into a microgravity environment. And I don't really want to get into the multi-megabucks kind of climate that you need in order to produce those sorts of experiments. So the alternative way of doing this is to use a cylindrical domain, and then basically you have the tropics heated and the poles cooled in the real planet, and we can mimic that in a qualitative sense at least by having two cylinders, an outer cylinder and an inner cylinder. We can heat the outer cylinder and cool the inner, and that's in a certain sense a little bit like sort of sitting yourself over the top of the pole of the Earth and then looking down on it, and then this is the sort of the polar regions and this is the tropics, and then something interesting will happen in between. This is what the real experiment actually looks like, and what actually happens, of course, if you play your cards right, is you observe a baroclinically unstable region with all sorts of complex instabilities that break out, and it's really the regime structure of that which in a sense provides some of the inspiration for what I'm going to talk about a little bit later in the talk. So this is The sort of laboratory system, it's been studied, as I say, fairly intensively on and off for the last 60 years or more. And we know for that system that there are a surprisingly small number of basic dimensionless parameters that you need to focus on. One of which is, they're all basically determining ratios of particular forces or particular terms in the equations of motion. So the first one is in relation to a measure of the viscous dissipation in the system, which you can measure with respect to the Coriolis accelerations. And so this allows us to define a thing called a Taylor number in a sort of generic sense here, where L is some horizontal length scale and mu is a viscosity, the kinematic viscosity, omega the rotation of the system. And this is what it actually is, where A and B are the inner and outer radii of our annular channel, and D is its depth. For historic reasons, it turns out to be this is the most sort of convenient combination of a Taylor number. And the other main parameter is some measure of the sort of so-called Rossby number, so the ratio of inertial to Coriolis forces. And if we use geometry and the geostrophic thermal wind, we can derive an appropriately defined parameter in terms of the parameters that we have in our control, and this is frequently referred to as the thermal Rossby number. So again, it's a combination of buoyancy forces and Coriolis forces that are essentially what this measures. So if we play that game, we can then basically run our experiment under a whole range of different conditions, and I guess this is kind of sort of well known in lots of textbooks now, but perhaps not necessarily as widely appreciated still as it might be. So we can create a kind of map of essentially what happens under which conditions, and this is a sort of schematic version of this. So we have the Taylor number along the horizontal axis. Note that it's a log scale. We have the stability parameter or thermal Rossby number in the vertical axis, again in logarithmic terms. And broadly speaking, we can break the whole regime space up into a series of different regions. So basically everywhere outside this sort of curved line here, we basically observe a very simple flow, and that's a simple overturning circulation with rising motion up the outer cylinder and sinking motion near the inner cylinder, and Coriolis effects basically transform the radially inward or outward motion into an azimuthal flow, and the flow essentially remains axisymmetric, and this is a stable, steady state of the whole system, and that's what we observe essentially all the way around here. Once you cross this boundary, however, interesting things start to happen, and then there's a whole sequence of events that take place whereby this axisymmetric flow becomes non-axisymmetric, but for large tracts of the parameter space, you find that it's occupied by these highly regular symmetric states, the so-called regular baroclinic wave regime. So this is baroclinic instability, fully manifest, and it's regular and highly symmetric, or periodically varying, in other words, highly ordered states for a lot of the region. And then as you head towards the bottom right-hand side, essentially at large Taylor number and small thermal Rossby number, the flow gets steadily more complicated and breaks down essentially ultimately into a sort of geostrophic turbulent flow. So that's been known for a very long time, but in fact if you look more closely, particularly at this sort of middle region, you find that there's even within that there's lots of substructure that you can identify. You can see different wave numbers and the regions over which they occur, some with sharp boundaries, some with not so sharp boundaries, and there are transitions from steady flows to periodically varying flows. That's what AV means. Amplitude vacillation means the amplitude of the wave will vary periodically on a particular time scale. Of course, this needs hundreds of experiments to actually map out exactly what happens, exactly where all the transitions take place. And what you'll notice here, there are many regions here where you have more than one solution listed. What that means is that these are intransitive states, that once you're in, say, a steady 3 flow, as it says here, 3s, then you'll keep the steady 3 flow, but if you initialize the flow by some other means, you may arrive at this point in parameter space with a steady 2 flow, and if that's the space, then for as long as you keep the experiment switched on, you will maintain that steady 2 flow. So these are two disconnected viable solutions that can coexist at a given point in parameter space. And basically the majority of parameter space seems to be occupied by these multiple states.
What is the Earth-like Taylor number? Isn't it just way too large from the diagram?
If you measure it with respect if you measure it with respect to molecular viscosity, yes, that's true. But whether that's a helpful way to measure it, I think is somewhat questionable, because molecular viscosity is not the only source of damping in the atmosphere, and I think that's one of the more interesting issues that I think we need to think about a little bit more carefully. But I'll say a little bit more about that in
the laboratory. It is.
Sorry?
In the laboratory, that is how you calculate.
That is how we calculate it in this instance. Yes. So molecular viscosity is the primary mechanism for dissipation.
In the laboratory, is the temperature difference between the inside and the outside walls, or is it from the top to the bottom?
It's the horizontal temperature difference. So it's between the vertical walls.
That's why you can absorb it into a generalised Rossby number, so you don't have a separate fruit number.
That's true. Yes. So you can define a separate Froude number if you want to.
So they're coupled together because the horizontal temperature difference is tied to the.
Well, it's because we're defining it with respect to the imposed temperature difference, not the temperature difference that actually ends up being set up in the geostrophic interior. So there are internal temperature differences that you can define whereby the flow sets up its own vertical stratification and so on in a way that is itself flow dependent. But what we're doing here in the experiment, it's convenient to use these external parameters as control parameters. Okay, well, it's just to reinforce the point. So multiple solutions, hysteresis, commonplace, and we have these well-defined regimes with sharp bifurcations or transitions between them. Okay, and this is just a little example of sort of a set of experiments where what we're doing here is actually looking at real-time measurements of velocity at a particular height, and this is the corresponding vorticity field associated with the, I think it may be this level, I can't remember. Yes, it is, yes. Unfortunately, I couldn't quite get the movies to sort of entirely synchronize. What we're doing here is we're starting the experiment at one particular rotation rate, and then every so often we increment the rotation rate downwards. So we're keeping the temperature gradient fixed across the system and gradually incrementing the temperature downwards. And what you'll see is, so every so often you see that at that point we've changed rotation rate. The flow has now become a periodically oscillating solution. You can see the magnitude of the wave is growing and decaying until at one point we go over a tipping point, just to anticipate you see it's happened on the right hand side, but that's because this movie is going a bit faster than this one. And so you can just see this one now has now made its transition. Now it's in a 2 state, and now it will keep that 2 state as we then continue to increment the rotation speed further downwards. So that's just an illustration of pushing the experiment over the edge of one of these transitions. And this is just to characterize one of these more chaotic states where what we're looking at here is the azimuthal wave number. So this is looking at a wave number 3 flow here and contouring the amplitude as a function of time. So you can see that the azimuthal spectrum of the temperature field is quite complicated. There are many harmonics and so on, but the amplitude will vary in a cyclic way, but the depth of the modulation varies with time, and it's that which essentially gives you the nature of a weakly chaotic flow, and that in turn modulates the heat transport in a way that we can actually see here, which again we can actually measure in real time in appropriate forms of the experiment. And that we can see lots of kind of effects that are familiar in the context of sort of simple dynamical systems. Here's an example of where we actually mapped out the existence of a homoclinic behavior, where you can see now we're varying the Taylor number in this case and looking at the period of vacillation, the period of oscillation of one of these waves. We can see that as we approach a critical value here, we can see that the period of the oscillation essentially dies off to all intents and purposes towards infinity at some finite value. This is Taylor number minus some critical value. So 0 in fact corresponds to a finite Taylor number at which essentially the period becomes more or less infinite. And this we believe is all part and parcel of how the flow makes a transition to chaotic behaviour, and there's another example of scaling behaviour, this time in a log-log sense against one of the other parameters.
Are those experiments at constant Rossby number?
These are probably not. They're probably varying the Rossby number as well. The easiest thing is actually to change the rotation speed, which of course changes both of those control parameters. So you're following a well-defined trajectory, but it's not necessarily horizontal. Okay, and we can also represent these in terms of the discontinuous changes in regime in terms of phase portraits. I'm just simply illustrating that these are things that we can actually determine and study in the lab. So we can go from a sort of simply periodic structure, which is a steady baroclinic wave, to one which is amplitude modulated but periodic, so produces beautiful torus-like attractors, to something which is more complicated and chaotic. And again, these occur at sort of well-defined bifurcations. So another concept that's of interest in trying to interpret some of the things that we see in experiments are the concepts of geostrophic turbulence, and in particular forms of geostrophic turbulence where we can see both upscale and downscale energy cascades. So I'm not going to sort of go into much detail here. This is really just to introduce the idea that there may be other dimensionless parameters that will be of interest here. So we're looking at applications of the Fjortov theorem in approximately 2D turbulence, or quasi-geostrophic turbulence, which seems to be a paradigm that seems to work reasonably well with at least some aspects of the experiments that we can look at. And we can consider the situation where the Rossby deformation radius is relatively small compared with the size of the apparatus, so you're effectively injecting energy at a certain relatively small scale, and there's enough room within the system to develop both an upscale energy cascade and a downscale entropy type cascade, at least in the classical kind of paradigm that has been around for a while. And is that going to change for me? Let's try again. Okay. So we can study the effects of this in the context of a beta plane by carrying out these experiments in an apparatus where we vary the depth of the experiment with radius. So this is an example of a cross-section to the apparatus where we can put conical boundaries on the system and introduce a radial gradient of depth, which acts, at least for a barotropic fluid. We can show that that's formally similar to a classical beta effect with a value of beta that depends on both the rotation, the depth of the system, and the slope. And in turn, we can then define a so-called Rhine's length scale, just related to the square root of u over beta, where u is some measure of the velocity.
What happens with the temperature gradient?
Sorry?
What happens with the temperature gradient? Is it there?
Well, the temperature gradient will affect the magnitude of the u that we generate in this case. But there are ways in which we can define an externally defined estimate of the Rhine scale based on applying thermal wind scale essentially as a measure of u, and that's where the temperature scale could come in.
But it's a barotropic fluid, or a baroclinic fluid, then your beta analogy breaks down.
It formally breaks down, but in practice we find that the baroclinic waves still behave in a dispersive manner in a way that at least qualitatively and semi-quantitatively reflects the beta that you see here.
If it's a two-layer fluid, yes. But if it's more stratified, you still find that?
Empirically, yes, we do.
On your
Yes.
previous picture, you said that the waves of deformation was fairly small, and so you presumably get to the regime where they're no longer so dispersive when the waves are larger scale than the radius of deformation. And once you get a length scale much larger than the radius of deformation, Rossby waves stop being dispersive.
Yes, right.
Did you reach that case or not? You said the LD was quite small compared to the length scale of the apparatus.
Oh, well it can be, but on the other hand, again, we can explore
You can do what you like.
both extremes
I'm
of
just thinking
of
the
that.
picture you showed, in that case, I'd have expected that to be significant because you have the
That particular, which picture do you mean, Mike? The
so you have an LD.
in this case, yes. What I'm showing is very
LD.
very schematically, yes.
In that case, I was expecting you to see this non-dispersive behaviour
You do, but on the other hand, if you've got a significant beta effect, then it tends to be accompanied by some non-trivial changes to the pattern of zonal flows. You do actually get jet formation, or at least the breakup of the flow into chains of parallel baroclinic zones, separated by a scale which is comparable to the Rhine scale.
Talk about alpha, well, certainly I've seen very convincing computations where you get some coherent vortices on the scale. The phase deformation is very small, it's smaller than the Rhine scale, then you get some coherent vortices.
Yeah, there are all sorts of sub-regimes with all of these things, and yes, indeed. I mean, one of the other parameters I'm coming on to is looking at the ratios of the Rhine scale with other length scales in the problem that will also give you different types of behaviour. Okay. Move. Right. So this is an example where we were looking at a situation with sloping boundaries, relatively fast rotation speeds, so the deformation radius is much smaller than the gap width, and also the effective Rhine scale is also smaller than the scale of the gap width. So we can characterize, or at least we can estimate a Rhine scale using a thermal wind scale, which gives you a parameter that now brings in the applied temperature difference. Now, this is an estimate. This is an externally defined parameter. It's not defined according to the internal scales. So you have to take that sort of on board. But nonetheless, this is, you can define a length scale by this means, which turns out to be not too bad a measure of the width of these individual baroclinic zones. You can see evidence here for at least 2 parallel baroclinic zones within this tank, and obviously in a much more complicated and less spatially ordered kind of flow. And in this case, the jet, you can regard this as a kind of multiple jet flow, at least a kind of incipient production of multiple jet structures, controlled by some sort of inverse cascades. The small deformation radius means that we have to work at relatively small values of this thermal Rossby number, so that we basically end up with the deformation radius being, in this case, less than the Rhine scale.
Well, so how steady? You've got lots of vortices. Just looking at it superficially, it doesn't look like multiple jets. It looks like lots of vortices.
Well, yes.
How steady are those things?
But they're vortices superimposed upon I mean, they're coexisting with a zonal flow that is not just a uniform zonal flow. If you actually take the time and zonal mean of the flow there, you will not see a single sort of zonal drift, but there are discrete peaks.
I'm just wondering how steady those disturbances were, or if you're just looking at a snapshot in that picture.
These are far from steady. They're actually continually changing and evolving. So this is more like a genuinely turbulent flow rather than one of these nice regular ordered structures.
How would this pattern depend on the Reynolds number?
On the what, sorry?
Reynolds number.
On the Reynolds number? Well, obviously the larger the Reynolds number, I suspect the stronger the jet formation would become. But in fact, the Reynolds number probably isn't necessarily the best measure of that. There are, well, perhaps I don't want to sort of get into too many of the complications right now, but this is something I'd be happy to talk about a little bit later on. There are a ratio of other scales. There is another scale which you can define, which is a little bit analogous to the Rhine scale, which is defined in terms of the spectral transfer of energy, the upscale spectral transfer of energy. And it's the ratio of those scales, in fact, that determines the strength of the jet, of the appearance of these jets, rather than necessarily the scales that I'm just introducing here.
There's one more question. Sorry, keep on. So is this an internal rate to deformation, effectively? Has this got rigid upper and lower boundaries?
This has rigid upper and lower boundaries in this case, yes.
There's external deformation.
So, yeah, there are very few circumstances in which the external deformation radius plays any significant role in most of these experiments.
Yeah, so I think the reason I'm slightly struggling to understand what you were saying was that I forgot there was probably infinite external deformation. deformation radius, effectively.
I suppose that's right,
Well,
yes.
that's correct.
Yeah.
It's like one of these sort of two, and then you've got an internal radius deformation depending on your temperature contrast within the fluid.
Yep. Yep.
Okay, well, so this issue about whether you get coherent vortices really depends on the small external deformation.
Ah,
So you're not in that case at all,
No,
and obviously the apparatus can't get into that case because of the way it's set up.
not the way it's set up, I guess. Yes, you'd have to design a slightly different
Yeah, so
experiment
that's
to
a sort
see
of,
that.
that's a sort of regime you can't really do with this. Okay, that explains it.
Okay, right. Okay, so in terms of the parameters that we might like so just to summarise, what I've defined here, I guess, are the two main sort of traditional control parameters for the experiment: the Taylor number and the thermal Rossby number. And we can also define other dimensionless numbers in relation to this estimate of the Rhine scale. And in fact, you can kind of estimate the number of baroclinic bands that you might get in this system from the ratio of the gap width of the system divided by this Rhine scale estimate. So I've called this thing a sort of NJ, or N sub J parameter. Now, the reason why I'm introducing this will become apparent in a minute, because we can now turn our attention now to a planetary atmosphere. Now, are there any of these sorts of insights that we could translate to characterising a planetary atmosphere? Well, we can certainly define a thermal Rossby number and even a Berger number in terms of vertical stratification, provided we can get some estimate of the temperature contrasts in the atmospheric system. We can also define a Rhine's length scale in the same way using the thermal wind scale, but now it turns out that on a sphere, this ratio is not independent of the thermal Rossby number, because if we actually look at how this relates to the thermal Rossby number itself, we see that this is it only basically scales with the radius of the planet and this thermal Rossby number. And so if we then produce this NJ parameter, we find that that's actually not independent of the thermal Rossby number. It's actually directly related there too. Finally, how do we define a dissipation parameter? Well, I mentioned before that there was this issue about not wanting to use molecular viscosity, but there are other dissipation mechanisms within a planetary atmosphere, either to do with radiative damping or to do with some other more generic kind of frictional processes, for which we can in principle define timescales associated with these processes, say a radiative timescale or a frictional damping timescale. And so we can define a kind of general dissipation parameter as just simply being 4 omega squared times the square of whichever is the minimum of those timescales. And that's really more or less conceptually the same as a Taylor number if we regard the parameter there as basically 4 omega squared times a viscous spin down timescale, and essentially you come out with something which is more or less the same conceptually as I'm listing here. So those are, I'm suggesting, are parameters that are worth exploring and fixing on and see where it gets us. So with those in mind, let's have a look at the solar system and see where that gets us. So if we plug in suitable numbers and for the horizontal temperature gradient, we basically have to use what we actually observe as the measured temperature variations. Then we get numbers which I won't defend these to the nth decimal place, but these are at least to within the right order of magnitude. So we see that the Earth is in a relatively small thermal Rossby number condition, relatively small Berger number, and relatively large sort of Taylor number equivalent based on either the radiative time constant or whatever you like to estimate as the frictional time constant in the atmosphere. Mars is roughly half the linear size of the Earth, but nonetheless rotates at the same speed. So not too surprisingly, it has a thermal Rossby number which is also small, but not quite so small as on the Earth. But nonetheless, the radiative time constant on Mars is very short. It's only on the order of 1 day. And so when you plug that in, then you get effectively a number here that is actually relatively small, and that's consequences of which I'll come back to. Venus and Titan, on the other hand, Titan is the largest satellite of Saturn, which is a sort of a planet-sized object with a substantial atmosphere, a 1.5 bar surface pressure nitrogen atmosphere, and is also a slow rotator. The satellite is in synchronous rotation with its orbit around Saturn, with a period of roughly 16 Earth days. And so we can determine it. Oops, sorry, come back. We can determine its value of thermal Rossby number, and these are essentially large numbers, much larger than 1, both theta and Berger number, but with this nj parameter obviously being relatively small, whereas on Earth this nj parameter is a bit bigger than 1, and on Mars it's roughly equal to 1. So that's where we lie. And the dissipation parameters for Venus and Titan are also large numbers. So these are relatively weakly dissipated systems, or weakly damped systems, as one might interpret. Well, what I'm going to show now is an example of where we've now tried to do in a numerical model what we have been doing for many years in the lab experiments. So what I'm showing here are some animations from a series of simulations where we've taken a simple general circulation model. So this is the University of Hamburg PUMA model. It's a simple spectral primitive equation model on a sphere, roughly 10 levels in the vertical, and it's a pseudo-spectral model. So these are up to, I think it's T1, I can't remember what it is, T100 and something. And what we've done is to force it with a background temperature field that essentially has a simple monotonic equator to pole temperature contrast and a stably stratified vertical distribution that essentially mimics more or less what we observe on Earth, and we relax the temperature field linearly towards that background temperature field. There's linear drag on the surface, but in all other respects it's just a highly idealized planet, no topography, and with kind of steady forcing.
Are you forcing this from below with the sea surface temperature gradient, or are you relaxing throughout the?
No, there's no sea surface. It's relaxed in a uniform way to the whole two-dimensional latitude, height, temperature structure. So it's a lot simpler than the real Earth in that sense. But nonetheless, it's a full primitive equation simulation. So
how fast do you relax it to the zonal mean?
It's on a period of I can't remember the exact number, but it's with a relaxation timescale of the order of 10 days, I think. But
No, I just want to get a feel.
I think it varies a little bit between these. And so what you're looking at here are the results that you get if you then keep the temperature forcing fixed, but you vary the rotation of the planet. And you vary not by a little bit, but by a large amount. It's because we want to cover roughly the same amount of parametric real estate as we do in our lab. So what I've shown here is the first series. So this is at the same rotation speed as the Earth. So it's an Earth-sized planet. And so you can see that this produces essentially a single baroclinic zone, more or less, with something like a wave number 6 or thereabouts, but a rather irregular, chaotic behaviour. And then what we're showing here is increasing the rotation speed. So this is increasing to twice the rotation speed of the Earth, 4 times and ultimately 8 times. And perhaps if I just go back and restart it, you can sort of see what's going on. So this is at twice the rotation speed. So now you can see some indication of 2 discrete baroclinic zones, each with their own trains of baroclinic activity, all on a smaller wavelength scale than we see when with the same rotation speed of the Earth. If I initialize that, then we see the other 3 activated. So this is the Earth's rotation. This is 4 times the Earth's rotation speed. So now you can see multiple jets, in fact, moving in different directions. So these are essentially eddy-forced structures produced by the eddy momentum fluxes. And at 8 omega, well, I'm not claiming that we're necessarily resolving all the structure here. This may be a T170 run, I think, which is about as high a resolution as we've gone up to so far. But you see this multiple jet-like structures, much more like the kind of patterns that we're used to seeing on the gas giant planets in the solar system, Jupiter and Saturn, than we would expect to see on a terrestrial planet. So that's what happens when we increase the rotation speed. If we decrease the rotation speed, then this is showing half the Earth's rotation, a quarter, an eighth and a 16th of the rotation speed. So you can see here we've got essentially much lower wave number structures, rather more coherent kind of behavior. And if we set the other ones going, so this is the half omega. Again, you see something like a wave number 5 pattern, but fairly regular and symmetrical, just migrating around the system. And then with these very slow rotators, we see essentially just a rather sort of irregular elliptical type of polar vortex structures with sort of fairly turbulent kind of or fairly chaotic kind of behaviors. So that's what you get if you take a simple atmospheric model and play around with some of the parameters over quite a wide range. So we already see quite distinct and different kinds of behavior. We can plot the relevant parameters for each of those runs, and so this is what we're showing here. So so this is omega over the rotation speed of the Earth. So from the 16th up to 8. So we can see that the range of thermal Rossby number ranges from something like 20 or so, which is somewhat similar to what we had found on Titan. So this is still not really Venus. Venus would be considerably more slowly rotating. Mars looks to be somewhere, well, actually, Mars is probably somewhere close to a half of the speed as we've got under these conditions. The Earth itself, as you've seen before, roughly the same as I showed for the Earth before. And then gradually, as we increase the rotation speed, theta gets smaller and smaller and smaller. And this NJ parameter then starts to get very big. And it's kind of interesting to pull out that the Earth itself lies at this kind of region where this parameter gets larger than 1 or crosses through 1 into this kind of interesting sort of multiple jet kind of regime.
Peter, if we were to not change the rotation rate of the planet, but change the pole equator temperature gradient, would we be going down in the same sense? Yeah. You could change theta. Oops. You could change this thermal Rossby number quite happily with that, but you wouldn't necessarily be changing this in quite the same way. So that's. Do you get regime shifts in that case? So if you don't change the right column, but you change the left. See these changes in the number of.
Almost certainly, but we haven't yet explored that in any detail.
Chris? Just ask something very similar to that. If we were to ramp up CO2 in the atmosphere,
right.
Do you have a feel for which of those parameters you might want to adjust just slightly to give an indication of how, especially you raise greenhouse gases, then what might we see in change?
Well, what would that do to the radiative equilibrium temperature difference from equator to pole? I mean, that's the question I think that.
So these
one needs
are
to.
questions.
Yeah.
Okay.
So actually, let me just finish this, because that's an issue that I'm going to come on to just to raise as a possible approach to this. Sorry.
Can I ask a question? Were there attempts to relate internal deformation radius to the number of jets? And I believe in your model it's a diagnostic problem, right? So it's part of the solution.
At the
In the
well,
interior.
there is a generic question with all of these things. It's on how do you define external control parameters as opposed to internal sort of scales that will emerge naturally within the flow. And it's not trivial actually to define those. So in practice, the theta actually is not a bad estimate to within a factor of 2 or so of the Berger number, which is the internal ratio of the radius to the deformation radius.
You've got the sort of same vertical stratification superposed on top, which is left the same.
Well, in the way that we're forcing these experiments, yes, the vertical stratification is prescribed. Well, at least the vertical stratification to which we are relaxing is prescribed.
And that's sort of characteristic of the current Earth, is it?
And that was, it was designed to be characteristic of at least the Earth's kind of troposphere up to the sort of lower stratosphere.
Yeah, so in this case, there is a well-defined internal deformation radius.
Oh yeah,
In the
yeah.
others.
Oh, I
Each
think
of
so.
this
Yeah,
is-
yeah, yeah. So I could also show you an internal Berger number within this table, and in fact, I think in the review article that I can tell people about, you can find a table like this has a bit more information in it. But given for a talk, I didn't feel I didn't want to sort of saturate you with just with tables and numbers.
I'm just curious whether your n sub j would scale in this internal Berger number.
That I haven't looked at systematically, but that's, there are many things that we could do but haven't yet done as part of this study. This is the sense in which this is a study in progress rather than with a well.
Typically, the
completed result.
disturbances you've shown us in the previous picture can get the whole way through the model atmosphere.
Sorry, say again.
You showed us very steady wave patterns and rather unstable looking wave patterns in your animations. Are those typically penetrating the hull?
They are usually domain filling structures. Yes, they're not very tightly restricted in the vertical. That's
right.
true.
I think in the real case that's also an issue. Obviously, you can't study it in the setup.
Yeah, they're not necessarily uniform amplitudes throughout.
I know
but they do have complicated structures, but they will penetrate. Yep. Okay. Okay. Well, then, just looking at some more diagnostics from these various runs. This is the zonal mean flow as a function of latitude and height in one hemisphere. This is showing everything. This is showing sort of 8, 4, 2, and 1 times the Earth's rotation speed, and then a half, a quarter, an eighth, and a 16th. And this is mainly just to bring out the kind of trends that we see, that if you start from the Earth and increase, then basically what happens is that the main mid-latitude jet that we're familiar with on Earth has a tendency to sort of split into at least 2, and then ultimately if you increase by a large factor in rotation speed, then it splits many times, and you end up with this sort of very clear multiple jet structure that is sort of equivalent barotropic in its form. Whereas if you reduce the rotation speed, then the main mid-latitude jet essentially tends to migrate towards the pole. So the equator here on the left, pole on the right, and so it tends to migrate towards the pole, and then basically stays there. I mean, once you get beyond a certain rotation speed, if you reduce it any further, it doesn't actually push things much further, because now essentially this is sort of more or less completely spanning the entire planet. And this is the corresponding temperature structure, where you can see that as you increase the rotation speed, essentially you produce a tight temperature structure with increased internal horizontal gradients. In fact, if you look very closely, you can even see some indication of little step-like structures starting to appear in the isotherms. Whereas if we reduce the temperature, reduce the rotation, then basically the horizontal temperature gradient reduces in the direction that at least is consistent with what we find on Venus, as I showed earlier on, with these almost flat isotherms all the way from equator to pole. And this is just looking at the eddy structures. So this is looking at zonal wave number versus latitude. And so here's the Earth, where we can see it's sort of somewhere between 2 and 6 sort of present, slightly varying latitude. So this is showing this tendency for the Earth's mid-latitude jet to be not just a single structure, but there's obviously more than one scale involved, with a systematic change in dominant wave number as you move in latitude. If we reduce the rotation speed, then this breaks up into discrete, almost monochromatic wave number structures. So a half and a quarter, it's down to wave number 2, essentially dominated. And then as we go to these very slowly rotating cases, then it's essentially dominated by planetary wave numbers 1 and 2, essentially corresponding to elliptical and sideways displacements of the polar vortex. Whereas at higher rotation speeds, essentially you start to see more and more evidence of multiple discrete trains of waves, and here you can see, in fact, if you look here, you can see actually multiple completely different bands of structures with dominated by different planetary wave numbers. So, just very briefly about the role and the origin of these large-scale eddies. There are systematic variations in the dominant mechanism that's at work in these simulations. So, baroclinic instability is clearly the main mechanism for producing these multiple eddies for relatively low thermal Rossby number situations. So this is essentially associated with transport of heat and PV. And there is this question as to what role these instabilities play in terms of controlling the effective stratification and the tropopause height and so on. Whereas at relatively low rotation speeds, for the thermal Rossby number being one or greater, or significantly greater than 1, it seems to be essentially a barotropic instability mechanism of this polar vortex that is what's dominant. And in fact, the transition, at least in the runs that we've been looking at, seems to occur at something like between a half and a quarter, or around about a quarter of the Earth's rotation speed. Essentially, baroclinic instability switches off, but the flow does not become axisymmetric. It becomes barotropically unstable rather than baroclinically unstable at these slow rotation rates. And then there are sort of these subsidiary questions as to whether the flows we observe are chaotic or coherent, and whether or not the inverse energy cascade plays any sort of role. So we're at the very beginning, I guess, of trying to explore the sort of parametric dependence of these sorts of questions. Just to note that on Earth, essentially, we see that baroclinic instability is well known to be pretty chaotic, although it's not completely chaotic because, of course, it's sort of restricted to regions of the planet, and we see reasonably well-defined length scales that appear. This is a kind of sort of index cycle structure that you can sometimes observe in the southern hemisphere, where continental contrasts are not quite so dominant as they are in the northern hemisphere. So you can sometimes see evidence of sort of incipient, sort of regular cyclic kind of behaviour that's at least reminiscent of some of the things that we see in these more slowly rotating situations. Whereas on Mars, we tend to see more evidence of coherent structures. This is actually the result of a data assimilation exercise, actually measuring weather systems on Mars from spacecraft measurements assimilated into our numerical general circulation model of Mars. So this is the inferred surface pressure patterns that you see around the northern hemisphere and in this case in the south there are no baroclinic disturbances. This is the thermal tide you can see migrating around with a pressure signature that we can deduce in the southern hemisphere. So this is southern summer, when baroclinic activity becomes much weaker on Mars. And it's been known really since the Viking landers in the late 1970s that baroclinic activity on Mars has a much more regular character. It's much more sort of cyclic with well-defined frequencies, and this is the corresponding temporal frequency that was observed from synoptic observations at the Martian surface by the Viking lander spacecraft in the early 1980s. And so you can see that you get this sort of quite coherent-looking behaviour for tens of days, for months at a time, effectively. Just thought it would be interesting just to draw some attention to this. This is some early work by Matt Collins, who I gather is a member of this study group, but perhaps whether or not he still cares to admit to having done this in his youth.
We're reminded.
When he was a member of my group in the 1990s, we did some experiments where we were just about getting our full physics general circulation model of the Martian atmosphere going, but some of the first tests that we carried out were done where we actually suppressed the diurnal cycle, so that we just ran the model with realistic radiation, but the radiation was averaged over the 24 hours, and so we essentially presented the same heating and cooling rates at all longitudes. And so this only reflected the latitudinal variation of the radiative balance, but nonetheless ran the model including a representation of the seasonal cycle. So this has a seasonal cycle but no diurnal cycle. And what we found was a highly surprising result. It was highly surprising to us at the time anyway. So this actually shows the signal that we diagnosed from the location of one of the Viking lander spacecraft. So we were trying to reproduce the time series of surface pressure variations as a function of season. And this is what we got without the diurnal cycle present. So we see that during a whole chunk of the year, essentially there is no weather, which is not inconsistent with what the Viking landers actually found. But then when we enter essentially Northern Hemisphere autumn, you start to see some signal, some fluctuations, which are essentially the onset of baroclinic waves. But the remarkable thing was that what we saw was actually a completely periodic signal. It was absolutely almost pure sinusoid that came out of this, showing that what we were generating for long periods of time was a single monochromatic baroclinic wave migrating around the planet and minding its own business until the parameters sort of changed with the seasonal cycle, and then essentially the baroclinic waves just died away. But within this, we found that if we ran this for multiple years, we wouldn't get exactly the same pattern every year. But in this case, you can see that we basically get the same frequency more or less the whole of the autumn, winter, spring season, with a little bit of sort of something happening around about there. But now the following year, essentially we get the same kind of behaviour initially, but then all of a sudden there's a transition, and we suddenly get a different frequency, a much lower frequency. And this turned out to be a flip from a wave number 2 state to a wave number 1 state. And so from here on out, we basically got a monochromatic wave number 1 state that was then sustained throughout the rest of the winter, essentially until it died away. And so, and yet the actual forcing, the prescribed radiation essentially was identical from one year to the next. So this is actually showing a sort of a random change between, well, we interpreted this as basically the system having two possible coexisting wave number solutions. And it was by random chance that we sustained one of these for the whole winter season on 1 year, but the next year, for reasons best known to itself, due to its some sort of internal chaotic behaviour, it flipped. I'm sorry?
Have the landers seen that?
No. Well, I'll come on to what the landers actually see in a moment. Okay. So what so this was running the model with no diurnal cycle. Now, when we then activated the diurnal cycle and repeated the experiment, what we saw was something completely different. So now we see, so this is 2 successive years. We see again during the northern summertime, we get no weather. The thickness of here is essentially a pressure signal associated with the diurnal tide. This is the diurnal cycle. But now we can see that the onset of autumn and winter, we see a weather signal, a synoptic weather signal, but now it looks much more irregular and chaotic. But nonetheless, if we perform a modal analysis, a singular value decomposition of the signal, bit of time series analysis, we find that you can characterize these signals as a superposition or an intermittent flipping between 2 fairly discrete patterns which correspond directly to the wave number 1 and the wave number 2 state. And what we interpret this as is that it's the diurnal cycle that actually induces sporadic transitions between these 2 discrete modes that the system can support.
What time series of these 2 patterns look like?
Let me show you. That's basically the detrended time series. And what we then do is take the principal components of, well, actually, because these are propagating structures, you have to take these in conjugate pairs and then look at the amplitudes of the 2 conjugate pairs. And that's what this shows here.
So you did complex zeros?
In effect, we didn't explicitly do it, but it's a related technique, essentially. And we can see that there is a kind of alternating between, when one pair is large, the other pair is small, and vice versa, although sometimes you see superpositions of the 2. And you can actually represent this in a sort of a pseudo phase space as well, and that's what we were trying to do here. So you could see 2 discrete centres with the system sort of fluctuating back and forth between the 2. So anyway, put that in essentially as an example of behaviour that you can see in what is otherwise a reasonably full physics GCM that has the surface topography and the thermal inertia and various other sort of fancy physics sort of thrown in. This is much more like a real GCM than a sort of simplified one. Okay, well I'll skip that since time is marching on. So
What one hears about the seasonality on Mars is that it consists largely of the atmosphere plating out at one pole or the other, and then subliming back into the atmosphere as the seasons change. And did your GCM have
it represents that. It's a slight over-exaggeration to say that that's all the seasonality is. The thermal seasonality is much larger actually, and I say only about 30% of the mass of the atmosphere partakes in this equated sort of pole-to-pole sort of mass condensation process, which sounds a lot, but meteorologically it's actually a lot less significant than the thermal seasonality, which is actually pretty dramatic. Okay, well this is just by way of suggesting other parameters. So there is this business about how we define an external control parameter that's analogous to the temperature that we impose between our cylinders in our experiment. And the kind of logical thing to use, I guess, is the radiative convective equilibrium equated to pole temperature contrast. This, of course, has been suggested by various people, including Isaac Held, I guess, who suggests that you can represent an estimate of the actual equated to pole temperature difference in a parameterized way, where you can parameterize this D parameter, which is in some respects a parameterization of the efficiency of heat transport by baroclinic eddies. And there are various ways of doing that, of course, as I guess many people are familiar. But there are other parameters that may well be interesting if we can. So the next phase in what we're hoping to do with our model exploration is to go the next step from just using prescribed temperatures and prescribed friction to putting in something that is, if you like, a kind of minimal general circulation model with some physically based representation of radiative transfer. But we want to do this in such a way that we're not representing any one composition of a particular planet. So the next step is presumably, we believe, to add something like a grey radiation scheme, or possibly a two-channel non-grey scheme that can allow the possibility of a greenhouse effect in a very simple-minded kind of way. Now again, this is not intended to be a realistic representation, but is intended to be a schematic realization, nonetheless, using some basic physics. And so we could then basically introduce additional parameters that are relating, for example, the total optical depth of the atmosphere to the surface, and then represent some measure of the grayness, which might be the ratio of the optical depth in the infrared to the optical depth in the visible, for example, as a very, very simple way of introducing at least some physically self-consistent representation of radiation. And that will then allow us to look at the effects of some of the orbital and rotational parameters, again in a physically consistent way. So that would allow us then also to explore the effects of the obliquity, the extent to which the rotation axis is tilted over with respect to the orbit. And obviously the orbital eccentricity is another parameter that would again be of interest. Now this is starting to map out a rather grand, sort of very ambitious sort of plan now to take this simplified but nonetheless physically self-consistent atmospheric system, and then mapping out a series of parametric directions that we might like to explore. And certainly within our present capabilities, we're not likely to explore all of this in great detail on anytime soon. But nonetheless, we hope to take the first steps in this direction during the coming year. So this is a direction that we're hoping to move in, essentially to try to map out at least a schematic, sort of semi-quantitative map of the various kind of circulation regimes that result from variations of these now physically sort of connected parameters. Okay, so just to draw things to a close so we can get some lunch. So we can, in principle, I believe, take the first steps in drawing a sort of regime diagram for at least schematic planetary atmospheric circulations. What I've done here is to at least somewhat tongue-in-cheek to actually put the planets of the solar system at least roughly in their appropriate places. Mars, I'm not entirely convinced is in the right place. I'm sure with its strong radiative damping should probably be further to the left at a somewhat lower value of this log Taylor number. And so you can see that large-scale structure and the style of the circulation I'm suggesting is determined largely by a relatively few set of key dimensionless parameters, which would include the thermal Rossby number and its corresponding Berger number, and measures of the Taylor numbers defined in terms of radiation and friction, but also probably including things like the obliquity and the ratios of optical depths and so on. And these include these multiple eddy-driven jet regimes, superrotation, polar vortices, etc. And that these dynamical regimes are almost certainly separated by, at least under some circumstances anyway, by these clear bifurcations at specific parameter values, which at least has some relevance, I hope you will agree, to some of these sort of questions of sudden climate change, although it may well be that the Earth is a long way from one of these very hugely catastrophic changes of regime, but nonetheless I hope are nevertheless of some interest. There is a review article on this which is just about to appear in Planetary and Space Science, which has a more sort of astronomical flavour to it perhaps than I've been saying here, but I guess that may be of interest to some maybe. And finally, the planetary lessons to be learnt from this, I think, are that this is I hope going to lead us to a suitable shopping list of parameters that we can go to the astronomers to look for and try to measure, such as the planetary size, its distance from the parent star, and its planetary rotation speed particularly, I think, is a very important quantity that the astronomers need to try to get a handle on if they can. Well, what does this tell us that's useful for understanding the climate of these extrasolar planets? Well, here's a suitable list. Okay, well, I think I've occupied your attention for more than enough time. Yeah, okay. You have to include habitability whenever you talk about planets, I'm afraid. But I'm going to skip over that very briefly, and thank you for your attention.
Questions?
Yes.
Yeah.
Okay. In the Earth, of course, we have orography and we have frictional torques, and those tend to be so chaotic they can be treated as random. Mm-hmm. And when you have a random variation in your parameter, such as rotation, you can completely change the nature of the attractor. And so I was wondering what would happen to your very detailed analysis if you were to put a multiplicative noise term in your equation.
That's an interesting question. I'm not sure anybody's played this sort of game with this kind of tool. I think that's a whole new ball game that we would obviously have to take into account. But putting topography into these models is by no means impossible.
Well, actually, what I was thinking of was looking at your tech experiment.
Oh, I see.
And
right.
Just putting a random rotation on it. And you could put the energy. You could somehow balance the amount of energy that was being put into your system by taking it out, or at least numerically, taking it out of your flow, and see what the stochastic system did to that.
The other way to do it would be to put some noise on the pole equator, temperature gradient you're imposing.
Well, we have been doing experiments of that sort, and I could perhaps sort of give you perhaps offline sort of
I would be more interested in knowing what happened to the stochastic variations of the rotation.
So this is sort of spinning it up to some rotation value and then introducing some random perturbation in the rotation speed. Is that what you
Yes.
Is that what you have in mind? That's technically perfectly possible. To some extent we sort of do that anyway because it's impossible to sort of maintain an absolutely fix.
No, but you have to have something
But-
that's
but this is
realistic size.
Yeah. Well, that's the point. So yeah, it's technically possible. Would you need to have non-axisymmetric topography as well to?
Well, I'm just
Look at the
thinking
effect
as a
that you're
very
interested
simple
in.
experiment. I
Mm.
mean, you could just have it random with time, but assume that the randomness is distributed throughout the entire system almost instantaneously, so that, you simply put wiggles in your rotation speed.
Yeah, the problem with doing it realistically is that of course you'll affect the boundary layers a lot,
That's the whole point.
but you may affect the rest of the flow relatively little. I think.
I don't think that's true, actually.
Depends
I
on the
think
time scales, doesn't it?
I mean,
what
you'd
ti-
be surprised how long a delta function correlation process can happen.
Mhm. Well, it's certainly something one could think about
And
trying out.
I'd be worried about that effect before I'd be worried about increasing the complexity of some of your other parameters, actually.
Mhm.
My humble opinion.
Okay, well, thank you.
Quick question. I mean, one message I think from this is that you really get the impression that we can trust models and the projections of these behaviours. So things you see in the lab, you can see in the models, and then of course that allows us to move the parameters and test things. You're just picking up on your comment that you would like to populate more space with making these simulations. I mean, obviously the same building as Mars Allen. I mean, is there some sort of client prediction.net equivalent experiment?
This thought has occurred to us, although I haven't yet discussed this with Miles in that sense. But yeah, especially if one could make it quite appealing, I would have thought to the punters if one were to sort of put a kind of extrasolar planet sort of angle on this, I suppose.
You look at the habitability zone as a function of all these parameters. You get lucky, you've got a habitable planet.
Yeah,
The one that got the parameters that work.
That's right. It'd be fascinating. Fascinating.
yeah, but that's an interesting suggestion. Yeah.
Any other questions? If not, we can break for lunch. That's brilliant. Thank you, Peter.
Thank you.